Alright, what's up guys? In this video, we're going to pick up some multivariable calculus. We're going to be talking about differentials here. So as to write the differential dw in terms of the differentials independent variable. So we're given a function here of several variables. We have four variables, u, x, y, and z. And that's just given by z plus 6u all over x plus y. Okay. So to find the differentials in terms of those independent variable, we use the following formula. It's just going to be dw is equal to the partial of f with respect to u du plus the partial of f with respect to x dx plus the partial of f with respect to y dy plus the partial with respect to z dz. And that's essentially how we're going to find the differential dw in terms of the independent variables, which would be the variables in here, which are u, x, y, and z. And that's just what we're given the function here. Okay, so it's pretty much just taking partial derivatives. So we got the partial of f with respect to u. Okay, so basically that's just the partial with respect to u for z plus 6u all over x plus y. Now, what you need to remember about the partial derivatives is that since in this case we're taking the partial with respect to u, we're treating all the other variables, which would be the x, the y, and the z, as constants. Okay. Now, what we can do to make this easier, and I highly recommend you guys doing this, to kind of make the partial differentiation a little easier for you, especially if you're learning it for the first time. Well, you should be doing it anyway, but you can actually do it in your head and not actually have to write it down. What you want to do is you want to pull out what our constants are going to be. So we can pull out a 1 over x plus y because we're treating as a constant. Now we're taking the partial with respect to u, so you may think, okay, well we can pull out the z. Well, we can't pull out the z because z plus 6u, that we're adding z and 6u, so I can't just pull out the z, but I can pull out the 1 over x plus y. And so now we just got our partial with respect to u, and we leave the z plus 6u on the inside. And then we take the partial derivative from there. So the partial of f with respect to u in this case, we'll be able to see what we're going to get. And so when we do it here, it looks like we're just going to get 6 over x plus y. So that'll be our partial of f with respect to u. The next thing that we need is the partial of f with respect to x now. So again, that's the partial with respect to x, or the partial derivative with respect to x for the function z plus 6u all over x plus y. Now, much like we did up here at the beginning, this time we're treating all other variables as constants. And the only difference is, like I said, we got 4 variables, which may be a little bit uncharacteristic because we normally just use 3, but the process doesn't differ. So we want to pull out all variables that we're treating as constants. So that would include the y, the z, and the u. So in that case, what we can do is we can essentially pull out the z plus 6u, and we want the partial with respect to x for 1 over x plus y. And then we'll have our constant multiple rule, which we'll use. So here, if we do the partial differentiation, the partial of f with respect to x here, looks like we're just going to get z plus u multiplied by negative 1 over x plus y squared if you differentiate, partial differentiate over on this side. Okay, so hopefully you're with me on that so far. So let's circle that. And we're going to go to another sheet to finish up the other two. So now let's deal with the partial of f with respect to y, which again is the partial with respect to y for our function, which was z plus 6u all over x plus y. Okay. Now, you should easily be able to see that the partial derivative with respect to y, or the partial of f with respect to y, it's going to be the exact same thing that it was for the partial of f with respect to x, because again, we could pull out a constant. The only constant in here is, in our case, that we could pull out would be, would be the z plus 6u, and that would just leave us with 1 over x plus y on the inside there, which we could take the partial of that with respect to y, and we're just going to get the exact same thing that we got for the other one. And so let's do that just as general. So we pull out the z plus 6u, and we want the partial with respect to y, 1 over x plus y. And if we do all that, we're going to get the same partial derivative that we got for x, which would be z plus 6u multiplied by negative 1 over x plus y squared. So you get the same thing there. Okay, and then our last one is what we need to do next. So now we need the partial of f with respect to z. Okay. So what would the partial derivative with respect to z be? Well, that's easily just going to be 1 over x plus y. Okay. And that would be your partial of f with respect to z. And that one was easy. Didn't have to write too much down for that one. So for our final answer, we just have to write the differential in terms of its independent variable, which were the variables that we were given on top. So it looks like we'll have dw, and it's just going to be equal to 6 over x plus y du. We're going to subtract that because we ended up, getting a negative. So in this case, if we do the simplification, we can go ahead and multiply that z plus 6u back on if you want. So it'd be z plus 6u all over x plus y squared. This would be dx. Hopefully I can fit it all in here. And then this would be minus, same thing. So this would be z plus 6u all over x plus y quantity squared dy. And then we're going to add that to 1 over x plus y dz if we take the partial with respect to z, which we did there. And that would be your differential dw expressed in terms of the independent variables that we had up on top. And that's how you do it. All right, so given that you're good with taking partial derivatives, shouldn't be too bad, but that's your answer. So let me know if you got any questions. I'll see you next time.